Hello, everyone. Today we're going to be talking about pseudoscientific claims. First, let's begin with a definition of pseudosciences. The word pseudoscience literally means false science, so that should give you a pretty good idea of what pseudosciences are like. But anyway, as a formal definition, I like this one. Pseudosciences are claims or topics that are presented so that they appear to be scientific, but which are not actually supported by the use of the scientific method. Last week, we discussed the key features of the scientific method, which were the use of systematic empirical evidence to test claims, that science is a public endeavor and is self-correcting, and that science involves the use of testable and falsifiable theories. So, pseudoscientific claims are ones that may appear scientific at first glance, or that might even claim to be branches of science, but that they're not actually supported by the use of the scientific method. I'm going to use the pseudoscientific practice of homeopathy to illustrate the main characteristics of pseudosciences. Homeopathy was founded by a man named Samuel Hahnemann back in 1807. Appreciate that back then our medical knowledge and practices were fairly primitive. Bloodletting was still common, while surgical equipment wasn't sterilized, and drugs like anesthesia hadn't been invented yet. So anyway, homeopathy is a method of curing disease based on two principles. The first is the law of similars, which says that the same substance that causes a disease in healthy people will cure those who are already afflicted with it. Let's say you arrive at the emergency room after suffering a severe allergic reaction to eating some salmon. Which would you prefer, a drug to treat the allergic reaction or more salmon? This isn't a rhetorical question. A true believer in homeopathy would choose more salmon, illustrating the law of similars. Now, if this was all there was to homeopathy, it would clearly be insane, as people who get more of a substance that causes an illness or disease would become worse or die. Fortunately, people who are treated with homeopathy don't get worse, but they also don't get any better. And the reason has to do with the second principle of homeopathy. So the second principle is the law of infinitesimals, which says that diluting the dose of a substance increases the magnitude of its drug effects. Drug effects mean the effect that a drug has on the body. So alcohol's main drug effect is to get you drunk. Tylenol's main drug effect is to relieve pain. So this feature says that the smaller the amount of the substance, the more effective it is. To make homeopathic cures, a small amount of the disease-causing substance is diluted by mixing a drop of it in 99 drops of water. Then, 1 drop of this mixture is removed, so this drop contains 99 parts water to 1 part substance. This process is then repeated. The 1 drop of mixture is added to 99 drops of water, and 1 drop of this new mixture, which is 0.01% substance, is extracted. However, they don't stop there. This process is then repeated an additional number of times, originally 28 more times when homeopathic remedies were first created. You'll often see 30C on homeopathic remedies. C stands for the dilution factor of 100, meaning you mix each new drop of mixture with 99 drops of water, and 30 stands for the number of times that this process is repeated. So you end up with an extremely diluted mixture, which is in line with this second feature, the law of infinitesimals, that the more the drug is diluted, the stronger its drug effects get. So to summarize, homeopathy is based on the idea that a patient can be cured of what ails them by giving them an extraordinarily diluted solution of a drug or substance that would, if given in higher dose, cause the symptoms from which the person is suffering. So, if someone is suffering from seizures, the treatment would be to give the patient a very, very small dose of a substance that causes seizures. If the patient has a headache, you would give them a very, very small amount of a substance that would cause a headache. So, with this in mind, let's look at some of the characteristics of pseudosciences, and we'll see how homeopathy stacks up. So again, what we're going to be discussing is some of the main characteristics of pseudosciences. These characteristics can help identify pseudoscientific claims or distinguish them from scientifically supported ones. So remember that pseudosciences appear to be scientific, but they typically lack the characteristics that make a field or approach truly scientific, and instead they display these characteristics. The first characteristic of pseudosciences is the use of scientific-sounding terms or jargon, but which are used in a vague or incorrect manner. So all sciences will have their own jargon or scientific technical terms. The key point of pseudosciences, though, is that when these terms are used, they are used in a vague or incorrect manner. So, pseudosciences use these terms to enhance their plausibility or to create a cover story that sounds scientific. But beneath the surface, there are contradictions, or these terms aren't used properly, or the concepts simply don't make any sense when you think about them. For example, homeopathy uses terms like dilution and molecules correctly, but discusses drug effects incorrectly and uses terms like water memory, which just don't make sense. The point then is that the terms used in homeopathy make it sound scientific and like a legitimate field of medicine. The issue is that, as we'll see, the way these terms are used either contradicts how they are used in chemistry and medicine, or they simply don't make any sense, like water memory. The second key characteristic of pseudosciences is a reliance on non-systematic empirical types of evidence, especially anecdotes, evidence from authority, and appeals to tradition. In the pseudoscientific field, if a therapeutic technique was successful for one person, that is taken as very strong evidence for its effectiveness. However, we talked about how things like the placebo effect and spontaneous recovery make anecdotes a very weak type of evidence when determining a treatment's effectiveness. As a result, a true science won't use testimonials as evidence. Also, appeals to authority or tradition are common in pseudosciences, but again, in true science, they aren't valued. For example, you'll often hear that a treatment is based on traditional or ancient Chinese wisdom, thus giving it legitimacy because it has withstood the test of time. However, the age of a treatment that has never been scientifically tested says nothing about its effectiveness. There's no reason to believe that older is better. Think about the changes in medicine in the past 200 years. Would you rather be treated with the traditional, ancient practices or newer ones? Same thing with psychology. Would you prefer treatments from the 1800s or newer therapies? No reason to think that older is better. Applying this characteristic to homeopathy, the best, maybe only evidence for homeopathy's effectiveness comes from anecdotes and statements of authority, as meta-analyses show that homeopathy is not effective. For example, if you go to this website, you'll see lots of testimonials from people who were apparently cured by homeopathic remedies. But scientific studies find the opposite. A good example of this is this meta-analysis that was conducted a couple of years ago. And here's a brief summary of it from a popular science blog. In this study, the authors reviewed a large number of studies that tested the effectiveness of homeopathic treatments, and they found that they were not more effective than a placebo on average. The third main characteristic of pseudosciences is little to no self-correction. This includes a lack of peer review, focusing on supporting rather than disconfirming evidence, and a tolerance of inconsistencies. So, one of the main characteristics of science is peer review, which is where other experts in an area review a study before it is published to make sure that faulty studies with lots of errors aren't published and become part of the discipline's knowledge base. Pseudosciences may have journals, but they aren't peer-reviewed, especially by true scientists. So, there are few preventative measures for faulty research being published. Another key feature of pseudosciences is that they focus on supporting evidence and ignore disconfirming evidence. So they ignore the misses and concentrate on the hits. A good non-homeopathic example of this feature is psychics and mediums. It is true that they might make accurate predictions from time to time, but if you also keep track of how many of their predictions are wrong, you'll start to realize that, hey, these guys can't really predict the future. For example, Sylvia Browne was a famous psychic who died a few years ago. You can go to this website, or you can Google Sylvia Browne predictions, but if you do, what you'll find is that while she might get a prediction right from time to time, which her believers will focus on, she also got many predictions wrong. Again, suggesting that she was not able to predict the future. And then the last point here is that pseudosciences are tolerant of inconsistencies, by which I mean different theories or fields believing opposite things. The idea here is that because sciences are constantly undergoing self-correction, inconsistencies don't last for long in sciences. However, because pseudosciences don't undergo self-correction, inconsistencies remain. So the presence of inconsistencies for a long period of time suggests that something is a pseudoscientific practice. For example, megavitamin therapy involves prescribing extra large doses of dietary supplements, vitamins, and minerals to increase their effectiveness. On the other hand, homeopathy involves diluting these ingredients to minuscule amounts to increase their effectiveness. The point is that these two approaches can't both be correct. Either small or large doses are more effective, but this inconsistency is allowed to remain because the critical tests are never performed, because both of these approaches are pseudoscientific. Another big inconsistency with homeopathy is that 30C medication is extremely unlikely to contain any of the original substance that was supposedly being able to cure the disease. Remember that 30C, which is the first dilution factor used in homeopathy and is still common nowadays, means that you mix 1 drop of the substance with 99 drops of pure water and extract 1 drop of this mixture. You then mix this 1 drop with 99 drops of pure water, extract 1 drop from this new mixture, and repeat this process a total of 28 more times. Now, I won't go into details, but based on our knowledge of chemistry, once you hit 12C, you have a 60% chance that your substance contains even 1 molecule of the original amount. Now, this information is from Wikipedia, but at a 30C concentration, the patient would need to consume 10 to the 41 pills, a billion times the mass of the Earth, or 10 to the 34 gallons of liquid remedy, 10 billion times the volume of the Earth, to consume a single molecule of the original substance. Right? This is a major inconsistency. How is a mixture supposed to cure an illness if it doesn't contain any of the actual drug? Also, to give you another comparison, 8C is the allowable concentration of arsenic in US drinking water. So if that amount of arsenic doesn't hurt you, it's unlikely that an incredibly small amount of any substance will help you. And then a final inconsistency is with dose effect curves in medicine, which show that diluting a substance always leads to weaker, not stronger drug effects, and this contradicts the law of infinitesimals in homeopathy. In my drugs and behavior class, I spend a lot of time talking about dose effect curves. These are graphs which depict the relationship between the drug dose and its drug effects. The most common type of dose effect curve is an S-shaped curve, which looks like this. What this curve basically shows is that the effectiveness of a drug increases as the drug dose increases. That is, small doses of alcohol or Tylenol will have little to no effect on you, while large doses will be more effective, at least up to a certain point. This is why 8C of arsenic is fine in drinking water, because that very small amount of arsenic won't have any effect on you. But again, the inconsistency with homeopathy is that it claims that the lower the dose of the drug, the stronger its drug effects will be, which again is inconsistent with everything we know about drugs and medicine. So, if you're going to buy homeopathic remedies, this is what I recommend you do to make sure that you don't overpay for your medication. The fourth main characteristic of pseudosciences is stagnation in the field, where the beliefs, knowledge, and claims do not change over time due to the lack of self-correction I discussed as the previous characteristic. Now, this is somewhat ironic, because scientists are often portrayed as close-minded people who rarely change their mind. However, as we discussed, one of the hallmarks of science is self-correction, that claims in science constantly change as new and better evidence is presented. Think about the common approaches to counseling and psychology. They constantly change over time as new evidence comes out about which is the best method of treating mental illness. This is not true of pseudosciences. They pick a claim and stick with it. And that's why, for example, these principles of homeopathy have stayed consistent for 200 years now. Now, to be fair, recently there have been some responses to the dilution criticisms that we've been talking about over the past couple of slides. The first response has been to reduce the dilution factor from 30C to 12C or 6C, meaning that you're more likely to get some of the medication in the final drug product. But it's still unlikely to contain an effective dose of the substance. At the molecular level, there are likely to be impurities, so even with a greatly reduced dilution factor, there's still a chance that you won't get any of the substance in the final remedy. Or if you did, it would probably still be too weak to do anything. Again, remember that arsenic is allowed at HC in US drinking water, and people don't often die from arsenic poisoning from drinking water in the US, despite the fact that they drink lots of water. So, If you see 10C or 8C or even 4C remedies, they're still extremely unlikely to contain an effective dose of this substance. Another response was to come up with the term water memory, which says that the water molecules remember what was once dissolved in it, even though none of the original substance remains in the 30C medications. So the claim is that, again, even these 30C or 12C or 6C medications retain their therapeutic value because the water in it remembers the chemicals that were originally mixed in it. The problem, of course, is that water memory would predict that water would have memories of other chemicals that were mixed in it, like sewerage, toxic chemicals, and other substances, making the therapeutic benefits of the remedy quite questionable. And if you'll bear with me, I like this cartoon a lot as well. One of the great things about homeopathy is that because the remedies don't actually do anything, there's no need to worry about any nasty side effects. Okay. Finally, let's go over a couple more miscellaneous characteristics of pseudoscience, and I'll go through these fairly quickly. So the first miscellaneous characteristic is that the practitioners get no or very little formal training. The point here is that if you can teach someone to perform your therapy over a weekend or a month, it's probably pseudoscientific. Scientists, as you all know, spend a lot of time getting trained because there's a lot to learn. 4 years to get a bachelor's degree, an additional 2 or 3 years to get a master's degree, or 5 years to get a doctorate degree. So, many practitioners of pseudosciences either have no formal training or it's quite short, a weekend or a month, suggesting that they don't have a lot to learn in their practice. A second miscellaneous characteristic of pseudosciences is the use of non-falsifiable hypotheses, one where no evidence can be presented to refute them. Remember we talked about testable and falsifiable theories in our class on the scientific method, and we said that scientific hypotheses must be testable and falsifiable. The issue is that some pseudoscientific claims are non-falsifiable, which means that no result can be presented to show that the claims are wrong. Now, this might seem like a strength, but it's actually a huge problem. For instance, practitioners of therapeutic touch claim that they can detect an energy field around people. This energy can then be used, they say, to diagnose and treat disease. The issue is that the most sophisticated instruments have been unable to detect this human energy field, suggesting it doesn't exist. However, instead of accepting this as evidence that it doesn't exist, proponents argue that this energy doesn't exist in the same physical universe that we experience, and thus it can't be measured. The issue then is that their response is a non-falsifiable hypothesis. There's nothing that can be done to show that this energy doesn't exist. And this would be poor evidence for science. It's like, wait, you want me to believe in something that I can't measure or show that it exists? But it's taken as a reasonable response in a pseudoscience. A third characteristic is failing to produce useful results and avoiding opportunities for scrutiny. So mediums, psychics who could predict the future, and psychic detectives weren't much help in predicting the September 11th attacks or finding Osama bin Laden afterwards. Think of how rich they'd actually be if they could tell the future and they could bet on the Super Bowl winners each year. Instead, these practitioners don't provide useful outcomes, suggesting that they are pseudoscientific. On the other hand, science provides new drugs and longer lifespans, cleaner sources of renewable energy, better technology and products, etc. For the second part, again, scientists are very clear about their methodologies so that others can test their procedures and try to replicate them. Pseudoscientific practitioners, on the other hand, avoid explaining how their methods work as much as possible, or they only use vague terms. Or they might say something like, you can't use normal methods to analyze what I do. And then the final miscellaneous characteristic that I'll mention is the reverse burden of proof, that pseudoscientists put the burden on others to disprove their claims rather than presenting strong evidence to support their claims. In science, the burden of proof rests on those making a claim, not the critic. That is, if I want you to believe my theory, then I have to provide you with evidence that it is true. Instead, pseudoscientific arguments often demand that a claim be accepted until skeptics can demonstrate that a claim is false. For example, someone might say, astrological horoscopes can predict a person's future, prove that they can't. The issue is that the burden of proof is being put on the skeptic to disprove the evidence, to disprove the claim, rather than on the horoscope believer to provide good evidence that horoscopes are actually accurate. Okay, that's all for me today.